Perfect. Yeah, as I said, thanks, Mark, for introducing me. I hope everybody has been staying safe. I'm really excited to be here to talk about how we monitor performance of mobile apps at Shopify. And hopefully by the end of this, you learn a little bit about mobile app monitoring in production, or maybe it spikes your interest regarding, mobile app development or performance engineering in general. So just a little bit of like introduction. For me, my name is Uday. I'm a senior production engineer at Shopify. I went to school at U Alberta. That's where I got my engineering degree from. I'm originally from India, but I've been living here for a while now. I've been working at Shopify for a little over 3.5 years, and I've been doing mobile development of some kind or the other over this time. If you are familiar with the Shopify apps, I've worked on our mobile Shopify app, which is the store management app that merchants use for running their stores and fulfilling their orders and managing their inventories. I've also worked on our buyer-facing app called Shop, which people can use for tracking their packages. So if you've ever bought anything online and you want to see whether it's getting delivered, like when is it getting delivered, or you want to connect with your favorite stores, you can use that app for that. But my current role in our React Native Foundations team involves me building shared packages, tooling, and patterns for all of our React Native apps. So today, as I said, I wanted to talk about how we specifically do performance monitoring for mobile apps. There's going to be a lot of general performance monitoring stuff as well that applies to other kinds of installable apps as well. So this will be applicable regardless of whether you're into mobile apps or not. So let's start with talking about why performance is important in the context of software. So the quality of software in general can be measured across different dimensions. You probably have heard about these kind of concepts in your other courses: reliability, security, efficiency, and size, and surprise performance. These are all important areas that you want to care about when building an app. We've all used apps that have just felt fun to use and they're good. Performance has probably played a key role in your perception of the quality of the app. Slow apps tend to feel bloated and annoying, and nobody wants to use them. And it doesn't matter how good your feature set is or how beautiful a certain animation looks. If your app doesn't work fast and let you do your thing in a way that doesn't want to make you pull your hair out, you will struggle with acquiring users or retaining them. And as we like to say it internally, I don't know if it's JML, Jean-Michel, who is our CTO, or Toby, one of the other said this, we must look at being fast as a feature. It's mission critical for most apps. It's not a nice to have. But before we can make things fast, we need to know what isn't fast. I'm sure you've all learned about algorithmic complexity in your classes, the big O notation, in other words. That is an important tool, among others, for assessing chunks of code in isolation and improving them. But more often than not, performance bottlenecks arise at more high-level systemic layers in any reasonable big app. For instance, the reason why a mobile screen, may be slow to render is not that it's using a big O of n squared algorithm for a code snippet instead of a big O log n. For items ranging between 100 to 1,000 or something, it barely makes a practical difference. But rather, it might be happening because a certain network call round trip is taking too long. Some operation is slow, and it's actually something happening on the backend side. So statically analyzing code may not always give you the big picture insight. Hence, for meaningful improvements, we first need to measure the status quo and figure out what's not making the cut. And then we can go deeper and use other tools at our disposal for figuring out why things might be choking. In other words, don't try to optimize prematurely. Profile to figure out what's not working and then dig deeper. Let's talk about some of the characteristics of what good performance profiling strategy can be. When we are thinking of how to profile an app, we want to make sure that we come up with a certain list of criteria. The first one is that it needs to be quantitative. When you're using a fast and robust app, it's snappy, things are loading fast. Inversely, you can probably tell when an app is not performing well. You'll see a lot of loading indicators, slow screen transitions, dropped frames. However, we need to be able to profile the performance in a quantitative way to be able to make any meaningful progress. You should be able to deterministically tell whether something's broken or not, or whether you're making progress in a scientific way. Otherwise, it's just anecdotal and you won't actually necessarily know that things are getting better or worse. Secondly, you also need a lot of data to get meaningful insights. It's really difficult to paint the full picture by just running the profiler once and building conclusions. One needs to account for all sorts of runtime scenarios, like the amount of memory while the app is running, disk space, the different kinds of like CPU specs that are available. You know, your apps are running on different Android phones and iOS phones. They all have like, they come in different price ranges and they all have different kinds of specifications. Or things like the number of other parallel apps or background services that might be running at the same time. So to get a clearer picture, we need to run these experiments again and again in all of these different situations and aggregate the data using a reliable statistical method like averages, medians, or percentiles. These different methods have their own pros and cons, but you pick one that works for your use case. A good way to capture all of these scenarios is to get telemetry in production. Nothing gets closer to real world scenarios than real world scenarios. This means that the app needs to continuously report this telemetry once they're deployed in the wild on users' devices. And then we can have some worker servers listening to this data coming from these devices, aggregating them and generating performance reports in an incremental fashion. Mark actually mentioned over our chat yesterday that there was a little bit of confusion in the class regarding the need of such telemetry in installable apps like desktop apps or mobile apps. So this is one example of how such apps like mobile apps still need this kind of monitoring. If you've ever pressed yes on consent boxes, such as, would you like to provide anonymized data to help make this app better? They're often talking about data of this kind. There's more data as well, but it's often of this category. Let's continue with our criteria for a good profiler. So the third one is that performance profiling should ideally also account for the requirement differences in different flows or products. Different products require different parts of the flows to be faster or slower than others, while they might be okay with some other ones being slower. Before giving the current status a grade, the profiling standard must be able to capture these differences in the requirements. Let me give an example of a couple apps that we work on in Shopify. Let's talk about point of sale. Point of sale is an app that is used in physical stores. That is the app that the staff members are using for helping people purchase goods when they visit their brick and mortar stores. Point of sale is used by staff members essentially. It's not an average user's app. You turn on point of sale first thing in the morning and you shut it down and closing the store. Because of this one-time boot nature of the app, point of sale is a little forgiving as compared to other general apps when it comes to boot times. It still needs to boot up fast, but it's okay if it takes a few minutes to do that if you want to pre-cache the store's inventory at that location. What it's not forgiving about is the checkout flows. Once booted, point of sale needs to be blazing fast. We are in the Black Friday week. This Friday is going to be Black Friday and next Monday, Cyber Monday. So there's going to be a lot of sales happening. So think of a door crasher Black Friday sale when COVID wasn't a thing, obviously. You have long lineups of frustrated buyers, stressed out staff members who are trying to check out people as soon as possible. The last thing you want to see is a long loading screen when trying to complete a transaction. But it's okay if the staff members are spending like a couple minutes in the morning just setting up the systems, if you have to make a trade-off here. But if you compare that with another app, Shop, for example, it is a more leisurely buyer engagement app. So Shop is used by everyday people like you and I sitting on their couch for browsing a new sweatshirt that's on sale by merchants like Cotton. Checkout speeds are important here because people still buy products, but it's slightly more forgiving on an average day. What's not forgiving are the boot times. If your user has to wait a few minutes to get beyond the initial loading splash screen, they will lose all interest in the app and move on to browsing at your competitor. So an A+ grade for boot times for Shop and point of sale will mean totally different things when it comes to actual millisecond values. Our profiling standard, whatever we end up using, needs to be aware of these kind of like requirement differences. And finally, the output from a profiling standard needs to be standardized so that you can compare reports across different flows in an app or across different apps made by your company. You should be able to tell whether a performance score of, say, 400 on an arbitrary scale is good or bad, or whether 400 in flow A means the same thing as 400 in flow B. You don't have to necessarily say that 400 means a load time of, say, 500 milliseconds, because that will go against the previous slide, the contextual element. but you can still say whether it's good or not, or how far off is it from your max ideal that you're trying to achieve in an app. So there's the previous slide and this one are kind of contradicting each other, but you can still accomplish like a middle ground here. One industry standard that is quite popular that we use at Shopify as well is called Apdex. It stands for Application Performance Index. The general idea with Apdex is that it gives you a consistent score that reflects the user's satisfaction with the performance of an app. You measure how long the subject flow takes, a subject flow of your app takes via stopwatch. You start the stopwatch when the flow starts and you end it when the flow stops. This hits the quantitative requirement that I mentioned. And you gather numerous instances of this data continuously and keep on aggregating it. You define what the acceptable thresholds are. You define what millisecond values qualify as satisfied and what are just tolerating, and while the other ones are frustrating and they're not making the cut. This is how you add a little bit of context and nuance regarding the specifics of your app. And as an output, Apdex gives you a unified score on a 0 to 1 scale, or sometimes on a 0 to 100 scale if you're using percentages. 0 on the scale is absolutely abysmal, 100 is the perfect ideal. And this is like allows you to standardize these results so you know that 90 is good. This final result is not that dissimilar to how you might be graded in school. You have different courses with different subject matters and complexities that you take over your schooling, but a score of 50% consistently means passing, I think, and a score of over 90% consistently means that you nailed it. Apdex is trying to do the same thing for apps. So let's talk about the 4 steps that I mentioned in detail. And how that can be used for generating these scores. So as I said, step 1 is to measure how long a certain flow is taking in a raw millisecond values. You need to define what the start and end milestone of your flow is. So start quite often corresponds to when the system receives an input signal conveying the user's intent to do something. Think of a button press or a card press or tapping a push notification or saying, hey, insert assistant name here. I'm not gonna do that in case that trips off your phones. And in the same flow, end often corresponds to when the system has reached the state that the user originally desired. In this state, the user can use the system to do what they wanted to. The screen is interactable again. So this delay is hence called the time to interactive, or TTI. Step 1 in generating Apdex scores for a flow is to measure its TTI. Let's look at this example. So I've been saying the word shop a few times. This is a GIF from the shop app. You press an order card in the first screen. You see there are like 2 order cards in the bottom half of that screen, and tapping that card takes you to the order summary screen that gives you what the order total was, what were the actual products that you bought. So in this case, in this flow, the TTI timer starts when the user presses the home card. That's when they're conveying their intent. And it ends when the shimmering loading indicators on the next screen are replaced with actual order summary contents. Note that a version of the screen is rendered when we display the loading indicators, the shimmering loading indicators as well. Loading indicators are valid UI components, like we're explicitly telling our app, show loading indicator. But that UI is not what the user desired, so it's not interactable. So we can't just end the timer the moment anything in that screen is loaded. We have to specifically tell our timer that it is now meaningfully rendered. We have a final version of the screen and end the timer now. The step 2 is to report this data. We have to have a continuous telemetry system that is reporting these TTI values to some kind of backend service. Once the millisecond values are recorded on the user's device using the stopwatch, you want to send them out to your servers ASAP. This allows you to process that data however you want to afterwards in an aggregated fashion. Note that we are not pre-processing the TTI values on the user's devices before sending them out to our data warehouses. Instead, we are sending the original values. I've said that a couple of times, but that's really important. This is done in this way for a few reasons. The Apdex formula, we'll soon see that, requires you to aggregate the counts. So you cannot do any meaningful computations to begin with just by a single event from that one device. And even if we were to do that, if we were to do any client-side processing, we will lose the original millisecond values. If we change our minds later regarding how we want to analyze our values, say we realize that Apdex isn't good enough, we will lose the crucial raw input. The TTI values are the most flexible raw numbers, so it's useful to keep it around in case we want to do any other kind of analysis in the future. So there are a lot of third-party services that can help you with this kind of telemetry. Like A couple names that I can think of are like Microsoft App Center Analytics or Google Firebase. These are some off-the-shelf solutions that you can plug into your apps. We at Shopify have built our own custom thing called Monorail for this. Step 3 is defining the thresholds. So for a given flow, you need to define what timing values can be deemed as satisfactory or tolerable. So if I'm just pulling numbers out of thin air, one may say that a TTI of less than 1 second is satisfactory, while that between 1 second and 4 seconds is tolerable. Anything below 4 seconds is just not good enough and can be deemed as frustrating. Note that I just came up with these numbers arbitrarily for this example, but sometimes that is a good enough starting point, even in practice. 1 second for that particular flow makes practical sense. When starting with Apdex, you may not want to over-engineer this step of the process. Just pick a reasonable number, document it so that you can refer back to it if needed. If in the future you see that your resulting Apdex scores are really good, but people are still leaving bad reviews, citing performance issues, you may want to tighten these thresholds retroactively and regenerate the scores given the new standards. As we discussed before, since we have the raw TTI millisecond values stored in our database anyway, it's a little forgiving. We can change our minds and change these thresholds later if we have to. And finally, the step 4 is to funnel the numbers through the actual equation. So this is the Apdex equation. So let's look at the parts to this. So A in this equation is the final Apdex score, on a 0 to 1 scale, the output that we care about. N satisfied is the number of TTI reports that fit in the satisfied threshold range. N tolerating is the same thing, but the number that fit in the tolerating threshold range. Note that there is a coefficient of 0.5 here. We're dividing it by 2. That means that the tolerating counts contribute half as much to the score as compared to the satisfied thing. This is acting as a penalty of sorts, that the performance was good enough, but it's not as good as we really wanted. And 0.5 is a reasonable penalty that the inventors of Apdex came up with. And N, the denominator there, is the total number of reports that we got. So it's N satisfied plus N tolerating plus the remaining N frustrating. So the higher the N satisfied count, the higher the Apdex score. The same applies to N tolerating, but as I said, it's only contributing half as much. N frustrating, which is part of the N without the suffix on the denominator, that is only increasing the denominator. So the more the frustrating counts you get, the smaller this fraction will become and you will decrease the score. Another insight here is that the perfect score of 1 is only achievable if all the TTI counts were satisfying. So if N satisfied equals N. So in that case, the fraction becomes 1. Similarly, the worst possible score of 0 is only possible if all the events went into the N frustrating category. You see that N frustrating is not even a term in the numerator, so the fraction becomes 0. So in practice, you will see the scores ranging between 0 and 1, or between 0 and 100 if you're looking at percentages. You just multiply with 100 to get that representation. So let's work through an example. Say you get 1,000 screen views for a given screen. Let's think about the shop example. You get 1,000 screen views of that screen in the past hour. Out of these 1,000, 600 met the satisfied threshold, 200 met the tolerating one, and the remaining 200 fell to the frustrating category. So plugging these numbers into the equation, you get 600, which was the satisfying, plus 0.5 times 200, 200 being the, what was the other one? The tolerating, and the remaining frustrating don't even count towards that. And you divide that by a total of 1,000 events, and you get a final score of 0.7. So here, your Apdex score of 70% says that it's quite decent. It's not as good as it can be. It's not 95%, but it's not as bad as, say, like 35%. So there's room for growth here. The interesting bit is that it is accounting for it is numerical, it is contextual because you define what these thresholds are, but the end result is still comparable. You can monitor its growth over time, and you can compare whether this flow, which has a score of 70%, how is it doing as compared to another flow that has a score of 80%. This means that the 70% one needs more work to make it like as good as the 80% one. Once you have these Apdex numbers, you can publish them on a dashboard that refreshes periodically. This is a screenshot from one of such internal dashboards that we have at Shopify. You can see that you can track these scores over time. We have these different green arrows pointing up saying that it has been growing, or the red ones with a downward arrow saying that we are noticing a regression here. You can also split them by different device types or regions or whatever split makes sense for your particular application and track them individually across all the flows. So that was it for Apdex in general. And so far what we talked about was applicable to all kinds of front-end apps, mobile, desktop, websites, etc. I want to switch gears and talk a bit about Apdex in the context of React Native apps, because that's what I do on in my daily job. React Native, if you're unfamiliar, is a cross-platform JavaScript mobile app development framework, which is the default for building mobile apps at Shopify. The general idea, you don't need to know the specifics for this lecture, but the general idea is that you write your code once in a shared programming language like JavaScript or TypeScript, and it runs on both iOS and Android. And actually, quite in the newer versions, it also runs on Windows, Mac, or in the browser now as well. So some of our biggest apps, Shop, Point of Sale, Ping, are all using React Native or in the process of being ported to React Native. And it has a lot of like community involvement as well. Facebook built it and they maintain it, but companies like Microsoft and Discord and Walmart and Wix and obviously Shopify are heavy investors. They contribute a lot in this open source project. So we going back to the 4-step process to generate Apdex scores, measuring TTI, continuous telemetry, defining the thresholds, and generating the scores using that equation. The last 3 of these 4 steps are pretty general. They will apply to all sorts of applications. The first one, measuring the actual milliseconds TTI values, that will vary depending on the nature of the app. So the React Native portion of that will vary in the TTI portion. So let's dig deeper into that a little bit. As for some initial, this is going to also act like a crash course into the basics of how React Native apps work. So feel free to ask me questions at the end of the thing if you have more questions about this. So just for some initial context, React Native apps have 2 main threads. Native, I'm assuming most people will be familiar with the concept of threading. Right, Mark? Okay. So yeah, React Native apps have, awesome. If you don't, we can talk about it after as well. React Native apps have 2 main threads, a native thread that is running Kotlin or Java code on Android, or it's running Swift or Objective-C code on iOS, and a parallel thread, the JavaScript thread, running the cross-platform code. The native thread on both the platforms is responsible for actually painting the final UI using the native view components. It is also responsible for capturing and listening to external events, such as button presses, push notifications, system subscriptions, and whatnot. This native thread gathers this information and sends it back to the JavaScript thread so that it can be processed in a cross-platform way. The JavaScript thread reacts to these events, processes the shared business logic, and generates the screen render instructions and sends them back to the native thread. So the idea is that you're trying to pull in the shared logic as much as possible in the JavaScript thread, but you're letting the native thread run the system-specific code. And this back and forth communication is happening over an inter-thread communication module, which in the context of React Native is just called the bridge. So in most React Native applications, the render pipeline can be modeled via this diagram that I try to do. Forgive my drawing skills, but I think I get the idea across. So the flow starts with some kind of button press or touch event that originates on the native thread. You see that touch event arrow coming from the bottom. This event gets queued up on the bridge and is eventually relayed to the JavaScript thread. There can be a little bit of latency here, depending on how busy your JavaScript thread was while it was processing whatever it was. There could be multiple button presses coming in, right? And the JavaScript thread needs to process all of them. So there might be a little bit of like latency building up here. That is because this bridge is kind of acting as a queue. It's a first in, first out FIFO queue of sorts. These events come in from the native thread and they keep on getting relayed to the JavaScript thread. So let's this blue block in the top JavaScript block is corresponding to that latency. Let's call it T-touch because that is the amount it took for the touch event to get acknowledged by the JavaScript thread. So once the JavaScript thread knows that there is this event, it will process that event in some kind of event handler routine. Think of an on button press callback if you've ever done any kind of UI app development. It's the same for Android, iOS, and web. This on button press will take some CPU time as well. So in this on button press, the framework tries to figure out what target screen it needs to render. It will try to render that JavaScript component and figure out what UI it will need to render once the next screen is mounted. It also figures out what network calls or what database calls it might need to be doing. So it's basically preparing a list of tasks that it will need to do once the next screen gets mounted up. Once the system knows what to show, such as a loading screen, and what to do in the meantime, such as fetch data, it cues the navigation animation and sends those instructions to the native thread. This is the orange block while it's like doing all of this pre-processing to figure out what it needs to do. And I'm calling that time T frozen, since the app is essentially kind of frozen while this is happening. It is figuring out what the next steps are supposed to be. So you're in an ideal application, you're trying to shrink this T frozen as much as possible, so the app keeps on going. This is, if you have ever seen a stutter in an application where you press a button and it takes a couple seconds for the animation to kick in, that's because that app hasn't optimized its orange T frozen block. The navigation animation and painting the loading indicator will also take some time. That's the pink bar, the TNAV. It's happening on the native thread. Notice that on the bottom bar. In parallel, the framework also starts fetching the resources that I was talking about, making the network calls and database calls. That's the green bar that is happening in parallel. So in the shop example, this is where the shop app was talking to the servers to fetch the order data. So these pink and green bars can theoretically be relatively longer or shorter than each other, but more often than not, data aggregation is usually slower than rendering the loading indicators, which makes sense. Making a network call is slower than painting a loading indicator. So in this example, I've shown the green bar to be slightly longer than the pink bar. But you can imagine that if a network call is like stupendously fast, the green bar may be shorter and you may not even see a loading indicator. That can happen in super fast applications or in applications that don't need to make a network call. You will just directly see the target screen without any intermediate step. But once the data is fetched, the JavaScript thread will prepare the final version of the screen. It will prepare the render instructions and send them back to the native thread to paint it. The native thread will paint this final interactable UI. That's the red bar. The top half of the red bar is the JavaScript thread preparing the shared render instructions, and the bottom half is the native thread executing those render instructions. And by the end, you have the final interactable UI. So the TTI in this context is the sum of all of these blue, orange, green, and red parts, green or pink, depending on whichever one is longer. So an Apdex client for React Native apps needs to, at the very minimum, be able to measure the TTI values for the different screens. A nice library would be able to assist you with profiling these finer time components as well, such as T-touch and T-data, since that will help app devs debug why a certain TTI value might be too high. For example, a high TTI value with T-data might indicate a slow network call. Remember from the original example, where you want to figure out whether it's you're broken the screen or whether it's a slow network call. So that can be learned by noticing the T-data to TTI ratio. Similarly, a high T-touch value could imply that your JavaScript thread is getting clogged up, is doing too much work. If your application is doing a lot of background jobs, that might be the case. Now the specifics of how we go about measuring these individual time components is probably out of scope for this presentation, but that's where the real fun and gnarly edge cases start happening. That also requires an understanding of the app lifecycles on the different OSs like iOS and Android, and a bit of understanding regarding how React Native framework works. A sneak peek, we have been working on a package internally, React Native Apdex, to help with this kind of stuff. It's still being developed, but it's not unlikely for us to open source it in the future. So that's a sneak peek into the fun work that we have been doing at Shopify. But yeah, that's basically all that I had. Thanks a lot for listening to me today.